So in this present lecture series of ours, which is titled as Computer Networks, presently we are exploring about the third layer from the bottom, which is the network layer. And in my last lecture we have looked into all the protocols which are kind of used, implemented or operated upon this network layer. Now our today's agenda is about routing algorithms of this network layer. Now when we say routing algorithm, so the connection goes like this, because main function of the network layer is to route the packets from the source machine to the destination one. And in most of the networks, these packets will definitely require multiple hops to to complete their journey. And actually the part of the network layer software which is responsible for deciding which output line an incoming packet should be transmitted on, this decision or this kind of functionality is basically related to routing. So routing, we can say it is the decision for that which particular output line an incoming packet is going to take. Now here can be various scenarios. So if the network uses datagrams internally, this decision must be made afresh for every arriving data packet, since the best route may have changed since the last time because of this kind of, we can say, the switching, the networking technique. But if the network is using virtual circuits internally, these routing decisions are need not to made for every arriving data packet, but rather these routing decisions will be made only when a new virtual circuit is being set up. So what kind of switching technique we are using, that actually determines the frequency of this routing algorithms or routing algorithms to be set up. So in case of this, when virtual circuits are being used internally, routing decisions, as I have told you, that they will be made only when a new virtual circuit is being set up, and thereafter all the data packets will just follow the route which is already kind of, we can say, established. This particular case, sometimes we can call it as a session routing, because a route remains in force for a particular kind of entire session. Now here we have actually kind of two terms, one is routing, another one is forwarding, and it is very important, it is very crucial to understand the distinction between these two terms, routing and forwarding. So routing is actually making the decision which route to take upon, and forwarding is the implementation, or we can say it is a process which happens when a packet arrives. So one can think of a router having two processes going on or implemented by virtue of it or implemented inside it. So one of them is going to handle each packet as the packet arrives, look up for the outgoing line, that which line is going to be the best, and how are we going to define this best, that I will tell you shortly. So looking for the all outgoing lines to use for, and these outgoing lines will be available in a table which is more commonly known as routing table, and the process is actually kind of forwarding. So routing decision is being taken place, and then forwarding happens. And other process which is responsible for filling in and updating the routing tables, and that's this is where your routing algorithms comes into play. So as I told you that all the information of the outgoing lines is to be will be present in the routing tables, and on the basis of that information your packet will be kind of forwarded. But one process which is essential here is to fill in that routing table with that information of outgoing lines, and also to update the routing table as and when required. So filling in the routing table, looking for the best line, and then forwarding. So this is we can say the whole process in a nutshell. Now when I say, which is the, kind of what all properties should be desirable in a routing algorithm. So here are the properties listed. One is correctness, another one is simplicity, robustness, stability, fairness and efficiency. Now, let us try to look upon all these properties in a brief manner. So, when we say correctness, obviously that algorithm has to be corrected and it is simple in order to implement. Robustness and stability is required because sometimes there can be havoc in case of all these routing tables, kind of we can say whatever is written in the routing table goes down. So, robustness and stability therefore are important, and so is the fairness and efficiency. Sometimes this should happen that the packets coming from a particular router or the packets exceeding one a particular size or something of that sort, all the packets or all the data which is coming on the coming on the line should be treated equally with fairness, and obviously the algorithm has to be efficient so that it can use whatever all the outgoing lines are there, those all lines can be used efficiency. Now see what happens if we talk about these properties. Let us assume a scenario in which a major network comes onto the air, and that major network, what are we expecting from that particular network? So, the expectation is that this network will run continuously for years without system wide failures. Now, this for a long period of time we are talking about, during that period there will be some hardware and failures of all kinds, and this is inevitable, this is going to happen despite of our maximum efforts. So, host, routers and lines will fail repeatedly, topology will be obviously kind of going to be changed many times. So, the routing algorithm should be able to cope up with all these changes, like changes in topology, changes in the amount of load which is kind of we can say traffic, and this is required. That means the coping mechanism of routing algorithm is required without requiring all the jobs, all the functions in all the host to be aborted. That means the host should be all the jobs in the host should not be aborted, and the routing algorithm should be able to adapt the changes in whether it is in topology or in traffic. So, that is why all these properties which we mentioned are actually desirable, that it should be correct, it should be simple, robustness and stability therefore are definitely required. Now, when we talk about till this point we understood what actually routing algorithm is and where are these routing algorithms are going to be used, what is the functionality. Now, before going into the details of these routing algorithms, let us see the bifurcation. So, these routing algorithms can be grouped into two major classes. One is the non-adaptive algorithms and another one is adaptive algorithms. Now, as the name indicates, non-adaptive is they are not able to adopt something. What is that? We will talk about it. And adaptive is which can kind of adopt. So, non-adaptive algorithms do not base their routing decisions on any measurements or any estimates of the current topology and the current traffic. Instead, the choice of a route which is used to get from one particular node, let us say I, to another particular node, let us say j, is computed in advance, that is computed in offline manner, and it is kind of downloaded onto the routers when the network is booted. So, that means no consideration of the current topology, no consideration of the current traffic, no changes, no modification according to these. The choice of the route is computed well in advance offline, and then it is downloaded to the routers where the network is going to be booted. So, basically kind of an we can say static routing. It is not going to respond to the failures even, but static routing is mostly useful in the situations in which the routing choice is kind of, we can say crystal clear. We do not have much of the dilemma in looking for the routing choices, and there are clear cut choices there. Looking into adaptive algorithms, so non-adaptive algorithm calculated well in advance and downloaded onto the router, no changes possible further. So, kind of an static mechanism. Looking into adaptive algorithm in contrast, where we say that they are able to change their routing decisions on the basis of network topology, and sometimes on the basis of changes in the network traffic as well. So, these adaptive algorithms will change their decisions to reflect the changes, which are done in the topology. So, if the topology is changed, routing decision may change, or it is kind of, we can say, allowed to change. And sometimes if kind of traffic is changing a lot, then in that situation also adaptive algorithm is going to change their routing decisions if required. So, on the basis of this information, we can say that these are dynamic routing algorithms, and the earlier one, which was the non-adaptive category, we have named them as static routing algorithms. Now, in static type of routing algorithms, we have seen that the information is collected, information of routing from a particular node I to another node j is calculated well in advance in an offline manner, and then it is downloaded onto the router. What about in this case? When we say dynamic routing algorithms, where are they going to get their information? So, they are going to get their information locally from the adjacent routers, maybe a single one, or from couple of them, or maybe from all the routers. And when they change the routes, that is when the topology changes, or when your traffic is going to change, then they need to look into what metric is used for optimization. That metric could be distance, number of hops, or the estimated transit time. We are going to talk about on these metrics of optimization soon. What we can say, these dynamic routing algorithms will be able to change their route as per the topology changes or as per the load changes. Fine. Talking about what kind of optimal routes we are looking for. So, the basic fundamental behind routing is to look for an optimal route. So, what is that optimal route, or how are we going to define that optimal route? So, this optimal route is kind of, we can say, or the concept of this optimal route is closely aligned to a principle which is known as optimality principle. This optimality principle was given by Bellman in 1957, and this is kind of, we can say, it is a general statement about optimal routes without kind of paying any attention to network topology or network traffic. So, optimality principle is general, that can get aligned with any type of network topology or any type of network traffic. So, what is that optimality principle? So, that optimality principle says that if a router, let us say J, is on the optimal path from the router I to router K, then the optimal path from J to K also falls along the same route. Now, this is if you can imagine the two routers I and K, and then there is a kind of intermediate router which is J, which is already on their path. So, the optimality principle says that if router J is on the optimal path from I to K, then the optimal path from J to K also falls along the same route. There is not going to be any other different optimal route from J to K. So, this is actually kind of, we can say, it is a simple optimality principle. Now, the set of optimal routes from all the sources to a given destination, if you can imagine that these set of optimal rules from all the sources to a given destination is going to form a tree which is rooted at the destination. So, root here is the tree, and all the kind of sources are going to be the set of roots will be there from source to that particular destination. So, that is going to be the path from the leaf to the root. So, whenever we are kind of talking about such a tree in which the routes are defined in the form of path from leaf to a destination, to a given destination, and this contains the optimal route from all sources. So, this is more specifically the term here which we are going to use is the sink tree. So, such a tree is called a sink tree, where the distance metric can be the number of hops or any other metric. It could be we can say delay, or it is going to be the length of the path or whatever it is. But the goal of all routing algorithms is to discover and use this sink tree for all the routers. So, one sink tree is or a particular sink tree is going to be made for all the paths for all the optimal routes from source to the given destination. Now, one thing is also very important here, that sink tree is not necessarily unique. Other trees with the same path length or with the same measurement of the metric, whichever we are going to take, may exist. And if we allow all the possible paths to be chosen, the tree will become a general structure which is known as DAG, directed acyclic graph. I am sure you all must be aware with this structure, which is a very common one in data structures or graph theory, and this is a directed, as I am saying, it is an acyclic graph. That means it is not having any loop. So, if we allow all the possible paths to be chosen, the tree becomes a more general structure called a DAG with no loops. Now, sink tree, whenever I am saying sink tree, it is indeed a tree, it is not going to contain any loop. So, each packet will be delivered within a finite and bounded number of hops, but this is I am repeating this line. So, this says your sink tree, which indeed is a tree and not having any loop, each packet will be delivered within a finite and bounded number of hops. Now, this is, we can say, it is a kind of theoretical assumption, or it is a kind of theoretical, it is an expectation which is not practical, which remains theoretical, because the optimality principle, nevertheless the optimality principle and the sink tree provide a benchmark against which other routing algorithms can be measured. So, this expectation that each packet will be delivered within a finite and bounded number of hops is somewhat theoretical, because the optimality principle here, the optimality principle and the sink tree provide a benchmark against which other routing algorithms can be measured. Now, when we talk about any kind of routing algorithm, what are we looking into? Actually, if you can see, we are going to deal sooner or later in context of routing algorithm, we are going to deal in shortest path algorithms. So, basically these shortest path algorithms are nothing but simple techniques for computing optimal paths given a complete picture of network, and these are the paths which we want to be which we want a distributed routing algorithm to find. And even though not all routers may know all the details of the network, so irrespective of this kind of this constraint that all the routers are having all the details of the networks, we actually want our routing algorithm to find this kind of shortest path, or we can say optimal path. So, basically how are we going to look into, or how are we going to, or a router is going to find that optimal path. So, in order to find that path, the idea is to build a graph of the network where, so graph as a structure, when I am talking about, it is having an edge and a node, where each node of the graph represents a router and each edge of the graph represents a communication link, or a link through which the data can be transferred. Now, in order to choose a route between a given pair of routers, the job of the algorithm which is remaining is to just find the shortest path between those two routers on this particular graph. So, the whole network is mapped in the form of a graph, and now we are looking for, and routers are the nodes here with the communication links as the edges of the graphs. And now what are we looking for? We are actually looking for shortest path between any two nodes which are router here. Now, how are we going to kind of we can say talk about this shortest path? How are we going to measure this path length? What all can be the metrics that we need to see? So, one way of measuring the path length is number of hops. So, how many hops it is going to take up while going from a particular router to another. So, let us see this figure which is being shown on the screen. So, let us say I am talking about a path in the figure which is going from A to B and from B to E. So, a path ABE is essentially equal to the path ABC if I am talking about the number of hops as the metric. So, the same number of hops in ABC, similar number of hops in ABE also. But let us say I am talking about another criteria of the shortest path algorithm, and that is the distance, the geographical distance. So, here if this figure is being kind of drawn onto the scale, or I am assuming the scale is right. So, here you can see the ABE is actually a shorter path as compared to ABC, because the distance between B and C is much larger than the distance between B and C, with the disclaimer that the graph is being drawn onto the scale. So, yes, geographical distance is another criteria. One is number of hops, in which these two paths ABE and ABC are same, but if we consider geographical distance as the criteria, they are not same, because the distance between B and C is much longer as compared to the distance between B and C. So, the two criteria which are very common that we have seen. Then another metrics besides this hops and physical distance are also possible. So, for example, you can label each edge with the mean delay of the standard test packet. So, that mean delay could be one of the metric, and the routing algorithm will choose the route which is obviously going to be the one with the minimum mean delay. And with this kind of graph labeling, the shortest path will be the fastest path rather than the path with the fewest edges or lesser number of kilometers. Here we are looking for the fastest path, and the labels on the edges can be computed as one example I have given as the as a function of mean delay. This could be a function of distance, bandwidth, average traffic, communication cost, then delays are there and other factors. No, by changing these weight functions of the edges, the algorithm would then compute the shortest path. So, all these can be kind of measures, or all these can be the metrics. So, bandwidth can be a metric, or a function of the bandwidth can be a metric, function of distance, how much is the average traffic on a particular link, that could be one of the metric, how much is the delay current or the mean delay which is calculated on the basis of test runs, how much is the communication cost, maybe in terms of kilometers, maybe in terms of actual cost. All these can serve as the metric in order to compute the shortest path. Now, in this lecture we actually looked into that what are we what are these routing algorithms and what do we mean by these shortest path algorithm. Several algorithms for computing the shortest path between two nodes of a graph are known, and here I have mentioned some of them. This is going to be our agenda for the upcoming lectures, that we are going to look into the details of all these algorithms, which are Dijkstra algorithm, Bellman-Ford algorithm and Flatt-Warshall algorithm. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next. Till then, take care. Goodbye.